Hi, AP Chemistry. It is Thursday afternoon. You did your volume of a gas lab this morning, and if you recall, I was telling you how I was getting myself confused because I'm teaching Chapter 5 and taping Chapter 6, so here I am taping Chapter 6. This is Part 2 of Section 2, and Section 2 covers calorimetry, enthalpy, and heat capacity. So this is the heat capacity portion of it. And what heat capacity basically doing is we are going to make a leap of faith, and we are going to relate temperature change to energy absorption or release of. So what we're going to do is we're going to assume that if the temperature rises, then the energy is being absorbed, and if the temperature falls, then the energy is being released. So it's kind of a leap of faith with heat capacity. There are three capacities, the first one being heat capacity. The symbol for heat capacity is a capital C. And heat capacity is the energy required to change the temperature of a substance by 1 degree Celsius. Notice that with heat capacity, it is not dependent on mass. So I'm going to write that up here, not dependent on mass. And the heat capacity, for example, of a piece of iron is 22.5 joules per degree Celsius. Now look at the units. Joules for every 1 degree Celsius. So iron will require 22.5 joules to raise the temperature 1 degree Celsius. Notice no mass in the units. Specific heat capacity you are familiar with. You did this in first year chemistry. Specific heat capacity is mass dependent. The symbol for specific heat capacity is S. The definition of specific heat capacity is the energy required to change the temperature of 1 gram of a substance 1 degree Celsius. Units for specific heat of iron is 0.45 joules per gram degree Celsius. And again, what does it mean? It means it takes 0.45 joules of energy for every 1 gram of iron to raise the temperature 1 degree Celsius. Technically speaking, it's a relatively low specific heat in comparison to, say, water, which is 4.184 joules per gram degree Celsius. It takes 4.184 joules for every 1 gram of water to raise it 1 degree Celsius. I mean, that's a much larger number, little more resistant to temperature change. Because it's got a larger specific heat. So in other words, this one, iron, is going to heat up faster. Molar heat capacity is the third and final definition for capacities. And just like the name says, it is dependent on moles of a substance. Therefore, it is dependent on mass of a substance. Molar heat capacity is the energy required to change the temperature of 1 mole of a substance by 1 degree Celsius. Molar heat capacity of iron is 25 joules per mole degree Celsius. So it takes 25 joules for every 1 mole of substance, 1 mole of iron, to raise the temperature 1 degree Celsius. Alright, heat capacity is basically the heat absorbed per temperature change. How much energy is absorbed to change the temperature 1 degree? Heat capacity with a capital C, there's the calculations and the units. Specific heat capacity is a small s. You're used to that. We call it MSAT for short. Units of joules per gram degree Celsius. Molar heat capacity, Q is equal to moles of times the molar heat capacity times the change in temperature. A couple of things to remember. Please remember that this little doodad right here means change in temperature. That's final minus initial. Q is, of course, heat, and you've had this one first year chemistry. You will notice that these two are very similar. It's just that this is moles of instead of mass of. Oh, notes. Specific heat capacity is on a per gram basis. Molar heat capacity is on a per mole basis. Q is heat. Yeah, joules. I mean, look at the units for all of them. Change in temperature, I just told you that part. Write this down. It's going to be a very simple problem. Most of this is going to be algebra related. Most of this is going to be a plug and chug situation. All right, it takes 78.2 joules to raise the temperature of 45.6 grams of lead by 13.3 degrees Celsius. Calculate the specific heat capacity and molar heat capacity of lead. So a couple of things I want to write down. First off, it gives me Q. And it gives me Q in the right units. Thank you, problem. That was very nice of you. It gives me the mass. And it doesn't make me calculate the change in temperature. It tells me the change in temperature already. Now, this isn't the gas law chapter. You can leave it in degrees Celsius. Again, look at the units. Use the units to your advantage. And the other thing I want you to realize, because you have to interpret a lot of these problems, raise the temperature. The lead is going to absorb. And its temperature is going to go up. All right. Let's see. First off, Q is equal to MSAT. And that's what we call it for short. We are finding specific heat capacity and algebraically manipulating the equation to solve for Q. I'll just fill in your numbers. Are they always going to be this easy? No. Some of them you might have to think about. Now, MSAT is very mass dependent. So you just plug this in, 3 sig figs, 3 sig figs, 3 sig figs, and you get a number. The specific heat of lead is 0.129 joules per gram degree Celsius. So now what was the other one? It was iron. If you recall, we said iron was 0.45. That means this guy heats up even faster. That means it takes about 0.129 joules for every 1 gram of lead to raise the temperature 1 degree Celsius. Okay, step number 2. It wants the molar heat capacity. Molar heat capacity is easy enough to do. First thing we have to do is we have to convert 45.6 grams of lead to moles of lead, and lead is 20719. So the moles of lead is 0.220 moles of lead. I want to find molar heat capacity, and it's going to be algebraically manipulated, and plug in, and you are going to get over, instead of where there was mass, there's now moles of. Everything else pretty much looks the same. And you get an answer, a much larger answer per mole for every 1 degree Celsius. So this means that it will take 26.7 joules for every 1 mole of lead to raise the temperature 1 degree Celsius. And a pretty big number, but it's per mole. Right, now let's see. You're not asking for heat capacity, but I want to just show you a little trick. Heat capacity. Alright, so I'm going to calculate it even though they didn't ask me for it. Again, this is the computation, so we'd find C, and Q of course is 78.2 joules and 13.3 degrees Celsius. So this is your traditional way of solving, and I get an answer of 5.88 and units of joules per degree Celsius. But I want you to know that I really just stick with MSAT in my head, and I basically just follow the units when I'm doing any other calculations. Okay, what do I mean, Mrs. G? What are you talking about, Mrs. G? Let's say that they tell you that they have a mass of 45.6 grams, and they give you specific heat capacity of 0.129 joules per gram degree Celsius, and they want heat capacity. So let's say the question says something like that. Well, think about it. Think about it intelligently. You got this staring you in the face. You want to calculate just heat capacity with units like that. What do you got to get rid of? You got to get rid of the grams. Well, how are you going to get rid of the grams? You multiply it by mass. That's going to cancel grams. So when I do these problems, you're going to find me following the units more than anything. And I get the same answer. So a lot of times, depending on what the problem gives you, you're going to watch me, you're going to find me following the units more than anything else. Alright, so this is lab. And you've done this lab before. You did it in first year chemistry, but in first year chemistry we assumed perfect calorimetry. We assumed a perfect styrofoam cup. This year we are not assuming a perfect styrofoam cup, a perfect insulator. We are going to assume this year that the styrofoam cup actually absorbs a certain amount of energy. So we're going to include it in our calculations. So what we're going to do is, this is technically the pre-lab. So we're going to find the heat capacity of the calorimeter, aka our styrofoam cup. And what it is the heat lost by the hot water is gained by the cool and the calorimeter. Now again, first year chemistry, you stopped right here. We did a perfect transfer of energy from the hot to the cool, end of story. This year, we're doing the cold water and the calorimeter, because in reality, your styrofoam cup is going to absorb some energy. Now, Zoomdahl likes to put the minus sign or the negative sign on the right, and I don't. As far as I'm concerned, the hot stuff will lose energy, and a loss of energy is a negative sign or a minus sign, whatever you want to call it. You need it for the math, because this is going to turn out to be one honkin' algebra problem. So you really need it for the math. What I have on the left here is the energy lost by the hot water. What I have on the right is the energy gained by the cold water and the calorimeter. And they are on the same side, because they are both going to heat up. These two are both going to heat up, because they are going to absorb energy. And who are they from? This guy. He's going to cool down. So we're going to substitute in a little of the capacities. There's the specific heat capacity and then the heat capacity for the calorimeter cup. And when we solve for C, this will give us our calorimeter constant. It's going to be a correction factor, which is the heat capacity of the calorimeter itself. So that means that whatever the hot stuff loses, some of it's going to go to the water and some of it's going to go to the calorimeter. This is really just basically algebra. This is a big whopping algebra problem, which I'm going to show you. All right. So here's my way of doing it, and my way of doing it's just a tad different than Zoomdall's, but I am comfortable with this method. The hot stuff's going to lose it to the cold water cup. That means MSAT of the hot stuff be equal to MSAT of the cold, and the heat capacity of the calorimeter. Now I leave my negative sign there. It's just algebra. Whatever makes you comfortable, but it's important to do the math. Alright, now the previous, what did it say? 50 mils of water at 90 degrees added to 50 mils of water at 20 degrees. Okay. I have 50 grams of hot water. 50 mils is 50 grams. Density of water is 1.00 gram per milliliter. Specific heat of water, put this one in your memory. You are going to use it a lot. Why? Because water is our favorite heat sink. What's a heat sink? It's going to absorb or release energy. It's going to be just perfect to use. We get lots of it. It's easy to take the temperature of the water, etc. Change in temperature. Final minus initial. The final temperature of all three things is 53 degrees Celsius. The initial temperature of the hot stuff is 90. 53 minus 90 gives me a negative 37.0. Again, it's just algebra. Cold stuff. 50 mils is 50 grams. Specific heat of water, again, 4.184 joules per gram degrees Celsius. Very resistant to change. Now, again, verbally, the final temperature of all three things is 53 degrees Celsius. The initial temperature of the cool water is 20. The difference between 53 and 20 is a positive 33 degrees Celsius. Here's my cool water. Now for the calorimeter part, this is my unknown, and I'm going to underline it because I'm going to get it lost. Now this is important. Change in temperature of the calorimeter. The cool water is in the calorimeter. So the cool water and the calorimeter must start out at the same temperature. So the cool water and the calorimeter start out at 20. all three end up at 53 degrees Celsius. So the cool stuff and the calorimeter will have the exact same change in temperature. And again, I'm going to box in my unknown because I'm going to lose it. I am trying to do my algebra right to calculate C, which is the heat capacity of my calorimeter. All right, algebra. I get 50 times 4.184 times a negative 37.01 times a negative. That gets me a positive value. Grams cancel. Degrees Celsius cancels in joules. 50 times 4.184 times 33. Gonna get 6,900 in joules. And I'm going to keep my unknown boxed in because of that, and I'm going to keep it a little larger. Here's my unknown, okay? Just algebra. Obviously, 7740 joules minus 6,900 joules over 33.0 degrees Celsius will be equal to the calorimeter constant. Comes out to be 25.4, and the correct units for the calorimeter constant. So what this means is the cup, or the calorimeter, coffee cup in our case, absorbs 25.4 joules for every 1 degree Celsius. Notice also, please, that there is no such thing as a negative molar heat capacity, or specific heat capacity. So if you decide not to throw in that negative sign, just be careful because it helps me to do the math correctly. All right, that's the end of part 2. On to part 3.